The famous Blackboard scene in Good Will Hunting sells mathematical genius by making one problem look impossible. But the actual difficulty of that problem is far below what the movie makes you feel. How does a standard undergraduate exercise get dressed up as a years-long mystery that only a miracle mind can crack? The movie uses three weapons: technical vocabulary that hides simple operations, the prestige of an MIT hallway, and camera cuts that erase the normal time math actually takes. By the end, you will see exactly how notation becomes costume design, and why the real barrier between you and that blackboard is not intelligence, but a handful of words you were never taught. In the first 60 words, the core question is this: how does the film turn ordinary graph theory into a genius test? The answer begins with what the symbols are actually asking. The problem asks for all homeomorphically irreducible trees with 10 vertices. Those words sound like a PhD defense, but once you translate them into plain English, the task becomes a drawing game. A tree in graph theory just means a collection of dots connected by lines where no path ever loops back to the start. Homeomorphically irreducible bans any dot with exactly two connections, which means you cannot have a skinny middle bend in a line. Isomorphic means same shape if you relabel the dots. The whole prompt translates to this: draw every distinct branching stick figure with 10 dots where no dot has exactly two lines coming out of it. That is the task. No calculus, no infinite series, no abstract algebra, just sketching, counting, and checking for duplicates. One small reality check before we go further. If you draw a star with one center dot and 9 outer dots, that is a valid answer. It is the simplest solution, and you just found it in 5 seconds. The movie never shows that step. It shows Matt Damon writing the final graphs in one unbroken, confident stroke, as if the answer arrived whole. That edit is the first lie. Real math is not instant. It is sketch, erase, recount, cross out the duplicate, and try again. The film compresses hours into seconds and sells the cut as proof of superhuman wiring. Now we build the full picture. Start with the notation itself. Greek letters, curly braces, subscripts, and uppercase script symbols make ordinary instructions look ceremonial. They act like a lab coat for chalk. The same problem written as dots and lines with no loops and no middle bends would not stop you in the hallway. But homeomorphically irreducible trees with 10 vertices sounds like it belongs in a journal, so your brain assumes it is beyond you before you even try to parse it. That assumption is the trap. The vocabulary is not there to clarify. It is there to filter. It separates people who have seen the words before from people who freeze at the sight of them. The filter is social, not logical. If you know what the terms mean, the difficulty drops instantly. If you do not, the board looks like a wall. The movie never acknowledges that gap. It frames Will Hunting as naturally brilliant, skipping over the years of training it takes to learn mathematical shorthand. Fluency gets sold as a biological gift, and the audience buys it because the scene never slows down to show the learning. Next, the handshaking rule. In any tree, every connection between two dots gets counted twice, once from each end. For 10 dots arranged in a tree, the total number of connections across all dots must add up to 18. That constraint is automatic. It is not a clever insight. It is just how trees work. But it cuts the problem down immediately. You cannot have 10 dots with 100 random connections. The number of possible shapes shrinks to a small list of cases you can check by hand. The one hub case gives you the star. One center, 9 leaves. The two hub case gives you 2 central dots connected by one line, and then you split the remaining leaves between them. A 5-5 split is one answer. A 6-4 split is another. A 7-3 split is a third. You keep going until the numbers stop making sense. Each case is just arithmetic and doodling. The entire solution space contains only 8 unique, valid shapes. That is not a years-long odyssey. That is an afternoon with a pencil and some scratch paper. The movie claims Professor Lambo took 2 years to solve it. That claim exists only to raise the stakes. In reality, this is a standard combinatorial exercise given to undergraduates in introductory graph theory. It is not trivial, but it is not a research problem either. It is a homework question with a finite answer. The professor who provided the math for the film, Patrick O'Donnell from MIT, chose it specifically because it looked impressive on a blackboard, but was accessible to students. The visual output matters. The final graphs look like branching circuits or alien runes, if you have never seen graph theory before. They carry an aesthetic of complexity. But the process that generates them is just systematic case checking. You list the possible hub counts, distribute the leaves, draw the shapes, and cross out any that are duplicates when you relabel the dots. It is methodical, not miraculous. The film hides that method entirely. Now compare it to the other problem Will solves earlier in the movie, the one that gets less attention. That problem involves a Fourier transform and matrix algebra. It is significantly harder than the tree problem. It requires more background, more steps, and more technical fluency. But it does not get the dramatic hallway reveal or the crowd of students staring in awe. The Blackboard problem gets the mythic treatment because it looks better on camera. The Greek letters and the branching diagrams photograph well. They signal genius to an audience that does not know the difference between a hard problem and a pretty one. The scene also benefits from location. An MIT hallway is not just a hallway. It is a stage. The polished slate, the brass fixtures, the echo of footsteps, all add a layer of prestige that primes the viewer to assume difficulty. If the same problem appeared on a whiteboard in a community college classroom, it would not carry the same weight. The setting does half the work. Authority does the rest. A professor publicly challenges the hallway with a math problem, and that act alone makes it feel sacred. The board becomes a test of worthiness, not just a question. People walk past it assuming it is beyond them, not because they tried and failed, but because the context told them to stay quiet. The movie never questions that context. It accepts the intimidation as natural, and then rewards the one character who ignores it. But ignoring intimidation is not the same as being smarter. It is just confidence. Confidence lets you try. Trying lets you learn. Learning lets you solve. The film skips that chain and sells the endpoint as a starting condition. The genius is already there, fully formed, waiting to be discovered. That is the fantasy. Real math is not like that. Real math is thousands of hours of vocabulary acquisition, pattern recognition, mistake correction, and incremental skill building. It is boring. It is slow. It does not make good cinema. So the movie cuts it out and leaves only the performance. Matt Damon walks up to the board, picks up the chalk, and writes. His posture is confident. His strokes are fast. He does not hesitate. He does not erase. The fluency reads as magic because the audience has no reference for what fluency actually costs. They see the output and assume the input must be supernatural. The script reinforces that reading. Other characters talk about Will as if he is broken or gifted or dangerous, always exceptional. The math becomes evidence of that exceptionality, not a skill he learned. The movie never shows him learning. It never shows him studying, practicing, or failing. It shows him cleaning floors and then solving problems that stumped professors. The gap between those two acts is left blank, and the audience fills it with mythology. The blank is the trap. It makes math feel like a secret language only some people can speak, and it makes those people feel like a different species. That feeling is not true. Graph theory is not a genetic gift. It is a branch of math with definitions, rules, and techniques you can learn the same way you learn anything else. The scariest words have the simplest meanings. Homeomorphic means same shape if you stretch it without cutting. Irreducible means you cannot simplify it further. Tree means no loops. Vertex means dot. Once you swap the symbols for plain words, the fear drops. The problem does not get easier, but it stops feeling impossible. That shift is everything. It is the difference between walking past the board and picking up the chalk. The movie never gives you that shift. It keeps the jargon intact and uses it as a prop. The audience is supposed to feel awed, not empowered. The scene is designed to celebrate genius, not to teach math. And it works. People remember the Blackboard. They remember Matt Damon writing in the empty hallway. They remember the idea that some minds are just built different. They do not remember the definitions. They do not try the problem themselves. The movie does not want them to. If they did, they would see the trick. The trick is this. The board is not a test of intelligence. It is a test of familiarity. If you know the vocabulary, you can parse the question. If you can parse the question, you can start sketching. If you sketch long enough, you will find the answers. There are only 8 of them. They are not hidden. They are just waiting for you to count carefully and check your work. The genius trap is not the math. It is the credibility theater around it. The jargon, the prestige, the speed, the aura. All of it works together to make ordinary academic work look like a miracle on cue. The film does not lie about the math itself. The problem is real. The graphs are correct, but it lies about what solving it means. It makes fluency look like magic and turns learning into an inheritance you either have or you do not. That is the trap. So, here is the direct answer to the question named at the start. How does the film turn ordinary graph theory into a genius test? It does it by hiding the method, compressing the time, keeping the jargon untranslated, and framing the solver as exceptional before he even picks up the chalk. The math is not the miracle. The miracle is the performance. The Blackboard is not proof of superhuman intelligence. It is proof that vocabulary, confidence, and context can make a standard homework problem look like a years-long mystery. The evidence eliminates the idea that this problem requires rare cognitive wiring. The result still leaves one thing unexplained: why the myth is so appealing. Why do we want to believe that genius is instant? That some people just see the answer while the rest of us stand in the hallway and stare? Maybe because it is easier than admitting that math is just another language, and languages take time. The film gives you a shortcut to awe. It skips the years and shows you the finish line. And that finish line feels good. It feels like witnessing something pure. But what you are actually witnessing is an editing trick, a vocabulary gap, and a very well-chosen homework problem. The reverence you feel is real. The math is real. The genius is the part that was added in post. If you want to check this yourself, look up the definition of a tree in graph theory. Then look up homeomorphic and irreducible. Then grab a piece of paper and start drawing 10-dot shapes with no loops and no two connection middles. You will find the star in under a minute. You will find the two hub splits in under 10. The rest will take longer, but not years. Just patience. That is the real lesson the movie never wanted to teach. Math is not a miracle. It is just work. And the board is not a wall. It is an invitation written in a language you were never taught to read. Once you learn the words, the door opens. The trap only works if you walk away. If this rewired how you see the chalkboard scenes in movies, try watching them again with the sound off, and ask what the symbols are actually saying.